Hey, what are you guys up to?
Nothing, just on a group chat.
Oh, that seems funny. Can you guys add me to it?
No, dude, it's only reserved for cool kids.
Oh, is it?
Let's discover how encryption secures data in most modern scenarios.
All modern day systems use public key encryption. The RSA algorithm, named after its creators, Rivest, Shamir, and Altman, is the most widely used method for encrypting and decrypting messages. The strength of RSA lies in the difficulty of factoring large numbers into their prime components. It's virtually impossible to reverse engineer the prime numbers from the product of their multiplication, ensuring the security of the RSA algorithm.
In RSA, each user has a private and a public key pair. The public key is made available to anyone that wants to send a message to the user and is used for encryption. This encrypted message can be decrypted only by the user using their private key. Let's say person A wants to send a message to person B. In this case, person A encrypts the message using the public key of person B and sends it. Person B uses their private key to decrypt this message. Let's understand the RSA algorithm with an example. We select two prime numbers, say 3 and 5, and calculate the product of them. 3 times 5 equal to 15. In addition, we calculate what is called a totient, which is 3 minus 1 times 5 minus 1 equal to 8. Next, we determine the private and the public key pair as shown in this figure. In this example, they both turn out to be 3. Let's say the sender wants to send the number 12 as the message. This message can be encrypted with the recipient's public key and can only be decrypted using the private key of the recipient. If anyone else tries to intercept the communication without access to the private key, they just end up with a jumbled mess of numbers.
Imagine trying to crack the code guarded by 313-digit prime numbers. It's like trying to find a needle in a haystack size of a galaxy. Regular computers are in for a 16 million year long run. Let's see how one would go about factoring a product of two primes. With n equal to 15, it's easy to guess factors as 3 and 5. But let's say we aren't able to. We start by guessing a number g which is less than 15 and doesn't share factors with it. Let's say we guess g equal to 2. Find the power of r such that 2 to the power of r modulo 15 yields a remainder of 1. If r is odd, guess another number. If r is even, in this case 4 is even, calculate the factors as shown. If they are non-prime factors, find GCD to compute prime factors. The key process that a quantum computer speeds up is finding r. Continuing with the example where g equal to 2 and n equal to 15, let's look at the remainders. The periodicity of the remainder gives us the value of r, and Shor's algorithm can be used on quantum computer to determine QFT, which gives us the periodicity. We implemented Shor's algorithm on the IBM quantum computer to determine the prime factors.